talk the future of computing with quantum computing. If we can see the slides, that would be perfect. But anyhow, I can tell you a little bit what we're going to talk about. First of all, I'm going to give you an overview and an introduction to the quantum computing topic and give you the basics, like what are the principles that are under the hood and how does it actually work with quantum mechanics. Thank you, Dries. And then we were going to actually show you 3 key areas where we're already seeing impactful things we can do with even the infancy of quantum computing. We're talking about quantum machine learning, quantum-inspired optimization, and then quantum security, which is an opportunity with quantum key distribution, but also a threat because it can break today's cryptography. My name is Rene. I'm Director of Global Innovation at Valorem Reply. We work with quantum computing, spatial computing, AI, computer vision, but actually much, much more. Full consulting agency, basically. And I'm also Microsoft Regional Director and MVP for quantum computing as well as mixed reality. So let's talk about quantum computing. The interesting part about quantum computing is, and I hate the word transformative or disruptive, but it's probably going to be the case with this technology, in fact. And it will have a huge impact in the 21st century because we can basically then solve problems we're facing today that are exponentially complex in polynomial or linear time. And this will be enabled by 2 things. Like when we talk quantum computing, it means radical new hardware. These quantum computers, these huge machines that would fit into this room, like huge things that are requiring cooling to almost 0 Kelvin, vacuum, and very specific capabilities so they don't get a lot of distraction. But also, you have to write your software in a different way because we're dealing with non-deterministic, and we have to use gates and circuits to define our problem. And we're really just at the beginning with this kind of stuff. But again, it will be quite interesting once this happens. Quantum computing is based on quantum mechanics. That's a discipline of physics that describes how the smallest particles in our universe behave. So atoms, or subatomic particles like electrons, photons, all of this, right? And when we're at this smallest scale, certain phenomena occur. And 2 of those I have here, which are very important that are being used with quantum computing. And the first one is superposition. When we're dealing with classical computers like this one here, right? As you all know, we're dealing with bits, right? 0 and 1, off or on. But when we're dealing with quantum computers, we're working with qubits. And the physical representation of a qubit could be an atom, like some used ionized atoms. You probably have heard about trapped ions. This is an implementation of a hardware for a quantum computer. Others use neutral atoms. Then you can also use photons and other subatomic particles. This is your representation of a qubit, basically. And you can put these in a state called superposition. This is done getting this particle in an excited state. We had some fun yesterday at the speakers' dinner talking about the excited state. But basically, once you get your qubit in an excited state, it's in the superposition. And then it cannot just be the value 0, 1. It can actually be anything in between and also all of this at the same time. Right? This is just assume that works. It does. But this is just a crazy concept to wrap your head around. It's really tough for us as humans to figure out, hey, what is this? What, I can have all these states at the same time. Yes, this is possible. So you see in the graphic here this sphere that is called a Bloch sphere. And so basically my value can be anything on that sphere, right? And so we can use this superposition state where we can represent multiple states at the same time. And this other principle is entanglement. And I'm going to show you a slide with a photographic proof of entanglement. But basically what this means is you can take one qubit and another qubit, put them together, and they become one unit. Although if you separate them, if you send one qubit in this direction, the other one this, they are still one unit. And so the changes you apply to one will also affect the other one. And so if you combine those, superposition and entanglement, multiple qubits, what you're basically getting at is you're getting an exponent in computational power, which means is if I'm adding more qubits, I can solve exponential problems in linear time. And that is very powerful for certain problems. And that's also a very important thing to say is quantum computers won't be replacing like your classical computer. right? We will still have those. And we will still have mobile phones with classical silicon-based computer chips. You've got to think about quantum computer more as a specific kind of an acceleration for very specific problems, right? Just like in the 1990s when GPUs, like graphics processing units, came out that are very good at dealing with large matrices and typical things you deal with in computer graphics. Or these days we have AI chips like VPUs, TPUs, tensor processing units that are very good for AI workloads. These QPUs, these quantum processing units, quantum computers, are very, very specific for certain problems, and I'm going to show you a couple of examples there. So, entanglement. This is a setup they did in 2019. It's an experiment where they basically, the result was the first photographic proof of entanglement. So what they did is, you see that little light source maybe here. So there was basically a laser, like 2 photons. They were shooting out 2 photons and entangled them. So 2 photons entangled, and then they did one thing, they split it up. One was sent in this direction, and the other one was sent in that direction. So the one went straight, the other one made a left turn. The one that made the left turn went through phase filter, which means basically your photon gets rotated, the orbit, right? It's, and you see it's like 45 degrees, 90, and so on. So again, initially entangled, then split up. One goes through the phase shifting. The other one, you see there's no phase shifting, but both are measured at the end with the cameras. And here's the result. These are both. So they both have the same phase shifting applied, as you can see here, right? Like this is one, this is the other one. Same kind of phase shifting with both of them. Although they were physically separate, kilometers apart, right? Again, crazy thing to wrap your head around. Actually, Einstein called this a spooky action at a distance. Einstein, when he lived, was always a very big skeptic of quantum mechanics in general. This was not his kind of stuff. But since all these smart people lived, like Heisenberg, Pauli, Bloch, and just to name a few, all of this had been proven in experiments. And this is the first photographic proof of entanglement. And just 2 days ago, these 3 guys actually got the Nobel Prize in Physics for making groundbreaking experiments to actually prove entanglement. They didn't work on the photographic proof I have just shown you. They did some other experiments that were earlier, a few decades ago. But the 3 guys, they got the Nobel Prize in Physics because this is the groundbreaking experiments where they have proven entanglement, which is the basis for quantum computing and quantum information science. Right? So you can see the impact that is getting there these days, right? So it's finally getting to the state, and people realize this is very important. So just a quick overview, what are some of the quantum computers out there? Again, you also have a lot of research universities working on this. In the Netherlands, TU Delft, for example, is working heavily on research with quantum computing hardware, with Microsoft. But you see IBM, Google, Intel, all of them, they have around 127 qubits, IBM, with their current quantum computer. And this year they want to release one which is around 400. D-Wave, you see, stands a little bit out, but they're using a different approach. They're using a thing called annealing, which I'm not going to dive too deep into this, but you have to imagine these are very specific problems you can only solve with annealing. The other one are more generic, gate model-based quantum computers. And Microsoft, also pretty active in that space, and Microsoft is actually working on 3 things here with Azure Quantum. Like, first of all, they're working on their own quantum computer research. Like I said, a large collaboration with TU Delft there, Technical University in Delft, where they're working on a very specific quantum computing architecture called topological qubits, where basically it's very tough to get it right, but once they get it right, they will have a very stable quantum computer. Because the problem with these quantum computers is you can keep this superposition only for a very short amount of time. We're talking nanoseconds. Right? We got to get to milliseconds and that kind of stuff. Because as soon as another particle hits your qubit in superposition, it will collapse, right? And so you want to keep it. That's why they cool them down to almost 0 Kelvin, vacuum, and so on. And the topological qubits approach that Microsoft is doing is very advanced, but it will take a long time. But they just had a breakthrough called where they're leveraging Majorana zero modes. Basically, this is the basis for this topological qubits stuff. So this is one piece they're doing, hardware research. The second one is Azure Quantum, which is basically quantum as a service. Because like, if you want to use quantum computers even the small ones we have today, they're super expensive, right? Cost millions. And so you cannot just buy it, but you can rent computing time on those via a cloud service. AWS is something similar, Bracket, and a couple of other vendors are working on this with quantum as a service. And the third thing here is, we all know the development tooling is pretty good with Visual Studio Code and all this stuff. And so they also have their own developer story and developer experience with Q#, a special programming language, which is better suited than Python, although you could also use Python, of course. A quantum development kit, a QDK, and then also they started a consortium, which is an open source initiative called QIR, the Quantum Intermediate Representation. Because you have to imagine, if you're now dealing with a quantum computer, you have to write these very specific instruction sets for the machine. There's another mic on here. So you write those very specific for the machine. Like just in the back in the days, I don't know, we are probably all too young for this, but if you worked on a mainframe or so, you had to really target that specific machine. The same is the case these days with quantum computers. That doesn't scale. And so you want to basically inject this quantum intermediate representation, just like you have with .NET or Java, right? Where you can it then targets the specific hardware. And it's much easier and scales much better. So what are the three key areas? I mentioned quantum optimization. We're going to talk about this. Quantum machine learning is also a topic we're going to talk about. And then quantum security, which is, like I said, an opportunity, but also a threat. But let's start with quantum machine learning. The challenge these days is, as you can see with these AI models, these large deep learning models that are being leveraged today, like GPT-3, it's ridiculous what the resources they use. Like just look at the cost here, right? Like training GPT-3 is around $5 to $10 million US just for the computational requirements that are needed. They're so big. And so the opportunity with quantum machine learning is, there is a research paper, I linked the paper here if you're interested in this. You can actually reduce this. And you can train it faster than a classical neural network with the same number of parameters. And that is very promising. As you can see on the graph, we have this quantum neural network, and you see the training, the loss value goes down much, much faster than your classical neural network, the red one here. They've proven this in the paper. It's really interesting and a lot of promise there. A very much active research topic. And we also did some experiments here with a classification model. And so this was with for the BMW quantum challenge, in fact. You see there's a crack here, right? So you want to detect the crack with AI computer vision classification. And what you can do is, because we just have these small quantum computers, we cannot represent the whole deep learning neural network as all of this in qubits. But we can take a slice out of this. And so what you see here, this is basically, just imagine this is all these artificial neural network. And at the end, before the output layer, you inject another hybrid layer where you get these 6 qubits in here. And these are the gates, basically. And with this, you're able to get faster results and also more precise results if you would not inject this quantum layer into this. And so you might wonder, why is this the case? Well, you can represent multiple states at the same time, right? In superposition. You can represent in your neuron, if you will, in the qubit, you can represent multiple states at the same time. So it's more efficient, and it's also faster, more efficient, but also more precise. And this is really interesting. If you want to get a little philosophical, right? If you think about it, like classical computers we're dealing with, they're digital, 0, 1. But our world is analog, right? Like it's not black and white, it's gray. And so the thing is, you can simulate that better. You can get closer to the nature, basically. So very promising approach, but very much in its infancy as well. A lot of research is ongoing in that field. There's a really interesting promise in terms of for these large AI models to make them less resource intensive. Quantum security. Like I said, it's an opportunity and a threat. What is the opportunity? The opportunity is very safe distribution of keys. Quantum key distribution, or short QKD, if you want to search for this. And here's an example. Alice and Bob, our good old friends, I guess you all know them. They want to transmit information between each other, and so they want to do this on a secure channel. And in order to do this, they could actually transmit a symmetric key over a quantum channel. So here's the example. Alice wants to send this shared key, the symmetric key, to Bob. But then there's Charlie, the bad guy, in between that want to do eavesdropping, right? He wants to steal the key. But Bob will always know if someone has stolen the key. Why is that the case? Because you transmit that key in superposition. And basically what this means is, if you want to measure it, if you want to get the result out of this quantum system, at the end you always have to measure it. And if you measure it, you basically know if someone measured it before you. So Bob will always know if someone has already looked into the key. And this is unbreakable. Like, this is a physical principle, right? If you're dealing with superposition, you have to measure it, and then the state will collapse. You probably heard about Schrödinger's cat, I guess. It's the same principle, basically, right? Like, you have this box, there's a cat inside of it, and there's a certain kind of a poison, right, and a radioactive element, and it will decay in 1 hour or something, and basically you will never know unless you look into the box, you will never know if the cat is dead or alive, so it basically is always at the same, it's both at the same state, just like Frick was saying, right, with the PHP example. It's dead and alive at the same time, and so this means it's in superposition, and we can use this principle for transmitting keys. So what they will do is, they will repeat this process until no one else looked at it before, and Bob is the first person that will measure it. The state will collapse on his end, and he will know, I'm the first one, so no one looked at it. I'm the first one that gets the shared key. Well, and then they can just use classical channel, encrypt the data with the key they transmitted, and do some good stuff there. This is an active research topic, but actually also in production already, like quantum key distribution. It's pretty interesting. So you see the key distribution hardware is available. You can buy these, basically. The challenge, though, is the length you can transmit that information. Japan reached a new record last year with a 600-kilometer long quantum key distribution network, wire-based. Because again, you cannot have a repeater in between, right? If you have a repeater in between, you will measure it. So the whole principle fails. So you need to have a direct connection. And so wireless transmission is interesting, but on Earth you have like atmospheric scattering. And a couple of governments, for example China, they have now an operational satellite with quantum key distribution. Like they launched a satellite, and I think in July or August it got operational. So basically there's a satellite orbiting that can do this quantum key distribution channel, which is just a few hundred kilometers, and there's not so much in between as if you would transmit it on Earth, right? And so this gets really interesting from that standpoint. True random number generator, you can also use these. You can actually buy little kind of USB sticks you can plug in. You get true random numbers, which is important for cryptography. Here on the screenshot, you see this. On the left-hand side, these are the pseudo-random numbers, right? These are the random numbers our classical computers can generate. And you see a certain pattern here. They're not really random. But if you're dealing with quantum mechanics, you get true random numbers. Because you just measure it, right? You get true random kind of information. And one interesting piece we're going to dive into the next slide is the threat with quantum security. And you want to implement things like cryptagility and DevSecOps in your organization to actually be prepared for this day. Because this is coming. Q-Day is coming. This is the quantum day. Some also say, if you're old enough like me, you probably learned the Y2K bug. There's another word now called the Y2Q, years to quantum. And this will be the day when we have a powerful enough quantum computer that can crack RSA and other, today's public private key asymmetric encryption algorithms very fast. So there's an algorithm, a quantum algorithm, because again, you have to write all your algorithms and your code in a different way. And there was this very smart person called Shor, and there's an algorithm called Shor's algorithm that can do prime number factorization, right? And with this, you can basically crack things like RSA and other asymmetric encryption algorithms. If you want to crack an RSA 204080 key today, it takes 300 trillion years on a classical computer. Impossible, right? That's the promise. This is why we always increase the key size, right? We make this more complex. If you have a quantum processor that is around 20 million noisy qubits, this can be done in 8 hours. And if you have a quantum computer that's had 4,099 logical or stable qubits, this can be done in 10 seconds. And this is coming. And experts say, there's a paper where they basically estimated it, they say 5 to 30 years. And exponential breakthroughs happen in technology sometimes, so I would rather estimate on the lower end of that. And like I said, huge investments from lots of governments, the US, China, but also the EU, making a lot of investments in quantum computing. Do you think they will tell us once they have it ready? They will just use it, right? And so, important thing, that's why crypto agility is important. Like, make sure you can quickly swap out these certificates. Because basically, RSA 204080, you have it everywhere. I mean, I don't need to tell you, right? HTTPS, all financial transaction messages, all of this is encrypted, and this can be cracked like this pretty soon. We'll take a little bit of time, but it's coming, and we got to prepare for this. Fortunately, there's also research into post-quantum cryptography. This is done by the NIST, National Institute for Standards in the US, and there are some pretty good algorithms that are quantum resilient, basically, that you cannot attack with a quantum computer, but they're not there yet in terms of like efficiency and so on, right? But just imagine how long it will take until all of this is exchanged, right? Like until all of these certificates and encryption algorithms are swapped out. This will take a long time. And so that's why this agility and DevSecOps is an important thing to keep in mind. Let's talk about quantum-inspired optimization. And you can keep it short, QIO. Basically, what you're dealing with is you're building your algorithms in a way that you can represent your problem as a quantum algorithm. But you can execute these on classical computers, on quantum simulators, if you will. What is optimization in general? Well, typical thing, you have a certain model, or you have a cost function. And what you want to do is you want to decrease the amount of energy you have to put into the system, but increase the output, typical optimization, right? What you often have to deal with is you have this multi-dimensional search space. Right here is just two-dimensional, but imagine the more attributes, the more dimensions. So it's a very multi-dimensional search space, and most optimization algorithms get stuck in a local minima. What you want to find is the global minima, right? And quantum algorithms are very good at this because they search all of this at the same, right? And you can leverage this already with quantum-inspired optimization on today's hardware. I'm going to show you an example in the next slides. But here are just a little bit of an overview. So you can, for example, fleet management, scheduling optimization, engineering, material science will be pretty interesting. But also chemistry and life science, especially protein folding. These very complex, multidimensional problems can be challenged and can be solved much faster with it. But also climate models, weather models, that kind of stuff. Yeah, huge, complex, multiple states at the same time can be solved, but also financial optimization like Monte Carlo optimization, portfolio optimization, risk analysis, and so on is really interesting. And when you go to these kind of quantum conferences these days, it's like you see a lot of folks from large banks are there. So they're aware of what's ongoing. And I heard actually a talk from one guy from a bank, I think it was, I don't recall which bank, US bank at least, basically said like banks that don't invest now into quantum computing, although it's in its infancy, will not have a market in 10 years. So that's basically what the realization is, and will be interesting. Here's a case we did with Enel. Enel is one of the largest energy grid providers in the world. I think the largest in Europe at least. So energy grid, I guess you know what it is, right? You have all these transformational stations, and also at clients, you have these smart meters and all of this stuff. And so they have around 20,000 field service workers that go out every day and need to visit client A, B, C, D. And if you know about computer science, this is the classical traveling salesman problem, right? NP complex problem. And you can optimize this, and you want to optimize this in such a way that you basically keep the shortest routes, right? It's a complex problem. There are certain optimization algorithms available, but it's pretty tough. And we implemented an algorithm called QUBO, which we call MegaQUBO. And QUBO stands for Quadratic Unconstrained Binary Optimization. It's basically a way to express your problem in a different way. And then you can run it on a quantum simulator, right? And this is what we're using here. We're using GPU arrays in the cloud, or FPGAs, and they can simulate a quantum computer. So basically, you have your problem statement defined in a quantum algorithm. You run this on a quantum simulator hardware, not a real quantum computer, and you still get better results. We get 20% time saving for this. Just imagine this for 20,000 folks, right? This is huge beneficial. And this is just with a simulator. Once we have powerful enough quantum computer with a few thousand qubits, this will just like fly. Another case is with Telecom Italia. It's, well, what we're dealing there, basically, think about cell towers, right? You have a certain frequency range, certain channels, and you want to optimize that there's not so much overlap between those, right? Because you have, like, if you connect with your phone to one of these cell towers, you want to minimize the overlap you have. Also, an optimization problem, and you can optimize this also with MegaQubo. You can basically split it up into these kind of problem and use this algorithm. We did also the AIRBUS Quantum Challenge. This was 2 years ago, 2020. There's 3 of my colleagues here from Machine Learning Reply. They won the AIRBUS Quantum Computing Challenge. And it was also optimization problem. Basically, as you can imagine, these airplanes, you have certain constraints, right? You cannot load too much stuff into the airplane. You have also physical constraint. It still needs to fly. And so you cannot put all the load on one side. So a lot of attributes, a lot of dimensions, basically, for the optimization problem. And we developed an optimization algorithm based on quantum algorithm that was pretty good and won the challenge. A bunch of scientific papers we also used. The last one is pretty new here, using Shor's algorithm on near-term quantum computers, where you can see a lot of stuff. The Qubits video series, I also want to point this out. There's a little video podcast I'm doing. Just recorded, I think, 50 episodes. And what I do there, as the name implies, like qubits, qubits, bite-sized pieces of quantum computing, is like 20 to 30-minute episodes. I invite an expert guest. We talk about a certain topic of quantum computing. And my goal is to make it approachable for folks that don't have a PhD in quantum physics, right? Like myself. So we want to make sure that it's not just stuck in these research labs anymore, but it's more approachable for everyone. And so you can just Google it or find it on YouTube, Qubits. It's a video podcast, so with video, but also we have it on the big podcast platforms with audio only as well. And with that, thank you so much for coming.
Thank you, René.